Now we need to discuss that last component, and that is the nucleophile. Generally speaking, a stronger base is also a stronger nucleophile. So for example, if we look at hydroxide versus water, the hydroxide ion we know is a much stronger base. Similarly, if you look at neutral alcohol versus its anion, the alkoxide is going to be the much stronger base, and therefore the hydroxide and the alkoxide are also the stronger nucleophiles. But there are cases when a strong base may not be a good nucleophile. An example of this is tert butoxide. So the name comes from the fact that it has a tertiary butyl group on it, and it's the butoxide ion. So it's the anion of tert butanol. And tert butanol, which I have written down here, has a pKa of around 18. Ethoxide, on the other hand, is the conjugate base of ethanol, which has a pKa of around 16. So you would actually expect that the tert butoxide would be a stronger base than ethoxide because it's coming from a weaker acid. And that is true if you were to look at its pKb value, you would see that tert butoxide is indeed a stronger base than is ethoxide. But tert butoxide is actually a weaker nucleophile than is ethoxide. Simply put, the reason that tert butoxide is not a good nucleophile is that it is bulky. It's too big. The basicity of a compound is related to equilibrium constants. So we're talking about KEQs, pKa's, pKb's. This is a thermodynamic property, and it's related to delta G, delta H kind of stuff. Nucleophilicity is related to the rate of the reaction. So we would say that that is a kinetic property of a substance, and this has to do with the rate law. Many times strong bases can also act quickly, meaning that a lot of times thermodynamically favored bases are also good nucleophiles. They can also be kinetically favored. But if they're bulky, they might be a good base, but not such a good nucleophile. So now we kind of need to look at why is that. Bulky bases like tert butoxide carry a lot of electron density around with them, and all of this electron density makes the base sluggish. And this really comes down to the fact that there's going to be a lot of steric repulsion. Hopefully you remember that term from when we looked at butane, and we saw in the eclipse conformations that you can have electron-electron repulsion when they are two methyl groups, for example, are across from one another. Anytime you have two electron clouds repelling each other through space, this is called a steric repulsion, and there's some strain there and energy cost to that. And bulky bases are going to have a lot of that steric strain associated with them. So when a base like tert butoxide tries to approach an electrophile like an alkyl halide, you get a lot of repulsion between the two because of the massive amount of electron density that's being carried around by this bulky base. Even though tert butoxide and ethoxide might be really good bases, they're both very good at just ripping protons off of things. Ethoxide is going to be a much stronger nucleophile. Tert butoxide is going to be a weak nucleophile. And this is a case of a non-nucleophilic base. Tert butoxide is going to be sort of the example of a non-nucleophilic base, a bulky base that we will use throughout both semesters of organic chemistry. There will be a couple of others introduced in the next chapter as well. As far as the SN1 reaction goes, remember this is what the rate law looks like. And so it actually does not depend on the nucleophile. So SN1 reactions will occur with weaker nucleophiles. They do not need strong nucleophiles to proceed. For example, if you were to run the following SN1 reaction under two different sets of conditions here, you would see that there would be no difference in rate. So both of these are starting with a tertiary substrate, and both of them are going to give the same product here that's highlighted in green, the organic product. However, we know that H2O, as we just discussed earlier, is a weaker nucleophile than is hydroxide ion. But in the case of the SN1 reaction, the rate is going to be the same in both of these conditions because there's no dependence in the rate law on the identity of that nucleophile.